All right. So today we will go through another example where we calculate the Clebsch-Gordon coefficients. But let me quickly recap what they actually mean. So again, there is two possible sets of bases in this tensor product space that one can write down. The first is the simultaneous eigenvectors of j square, j1 square, j2 square, and jz. Give me a second, this is sharing. And the second are the simultaneous eigenvectors of j1 square, j2 square, and j1z and j2z. Okay, so j square, jz, j1 square, j2 square, this set of operators, and this eigenvectors we have labeled as j1, j2, jm, or the simultaneous eigenvectors of j1 square, j2 square, j1z, and j2z. This set of eigenvectors, which we will call j1, j2, m1, m2. Okay. Now, as a practical matter, sometimes writing these in terms of this big symbols can be a little confusing. So I'll usually shorten this to jm, and I will shorten this to m1, m2. Okay. So based on the context, you should be able to figure out which is which. But in case it gets confusing, please stop me and we can switch back to the original notation. This is only done to minimize, writing and making sure things, aren't too unwieldy. All right. So how do you actually calculate Clebsch-Gordon coefficients? So first, let us actually remind ourselves what are Clebsch-Gordon coefficients. Well, I can always do a basis transformation that takes me from one set of bases to the other set of bases. So Clebsch-Gordon coefficients are basically the coefficients of this transformation, right? So I write the J1, J2, Jm basis. M1 goes from minus J1 to plus J1. M2 goes from minus J2 to plus J2. J1, J2, M1, M2, J1, J2, M1, M2. Okay. So this overlap is the definition of Clebsch-Gordon coefficients. Okay. So this is what we need to calculate. Once we calculate this, this boxed equation would make more sense. In what sense is this a direct sum of all these different j's? Okay. So there is one very important property. There's a couple of important properties of the Clebsch-Gordon coefficient. Some of them we will explore more in a problem sheet. One important property that we will use in today's lecture is that these coefficients are zero unless m1 plus m2 equals m. Okay. In fact, this is already known to you because you know that jz equals j1z plus j2z. But knowing this should, at least we can roughly guess that m1 plus m2 should be equal to m, but there is also a way to formally show that this has to be true. The way you show this has to be true is you first construct the null operator jz minus j1z minus j2z, right? So this is a null operator in the sense that since jz is a sum of these two guys, this operator obviously has to be equal to 0. Okay. So you calculate, you sandwich this null operator between these two, this bra and this ket. So you peel the CG coefficients J1, J2, M1, M2, and you thrust this null operator between them, Jz minus J1z minus J2z, J1, J2, Jm. Okay, and now you have to be careful as to which operator acts on which side. Now, these are both Hermitian matrices, so I can always act them on the left or the right with impunity. Excuse me. Notice that I cannot take Jz and act it on the, I cannot take J1z and act it on the right, Because J1, J2, Jm is not an eigenstate of J1z. It is the eigenstate, however, of Jz with eigenvalue m. Similarly, I can take J1z or J2z and act it on the left because these are both eigenvectors of J1, J2, M1, M2 are eigenvectors of J1z and J2z with eigenvalues M1 and M2 respectively. So if you do this, this matrix element turns out to be, and this is equal to 0 because we are calculating basically something relating to a null operator. So this tells me that Jz acting on the left, on the right is M, J1z acting on the left is M1, J2z acting on the left is M2 times J1, J2, M1, M2, J1, J2, Jm is 0. This is basically M minus M1 minus M2 times the Clebsch-Gordon coefficient. This has to be equal to 0. Okay. So if M is not equal to M1 plus M2, then the only way this equation can be satisfied is if the Clebsch-Gordon coefficient itself is 0. Okay. So this tells us, this implies that J1, J2, M1, M2, J1, J2, Jm. So you can sort of also understand why we need a shorthand notation, because writing this every time out is a pain, is 0 unless M equals M1 plus M2. Okay, so the sort of a common sense guess that you made based on the definition of the Jz equals J1z plus J2z turns out to be actually true. Okay, so this is a selection rule. And using this, we can actually get far in understanding what these Clebsch-Gordon coefficients actually are for every particular problem. There is actually a specific way in which you progress calculating the Clebsch-Gordon coefficients. And I will illustrate what this means. I also encourage you to go back and look at the last lecture and see how we did this for the addition of 2 spin half. Here I will sketch what this means for the addition of spin half and spin 1. Okay, so excuse me. I will take the example J1 equals half and J2 equals 1. And you already know that J can be any value from J1 minus J2 to J1 plus J2 in multiples in steps of 1. Okay, so in that case, it turns out to be J can be equal to either half, that is 1 minus half, modulus of half minus 1 rather, to 1 plus half, which is 3 half. Okay, and there can be no other states possible because 3 half minus 1 half is already 1. So we have exhausted all possible values of J. Okay, so first let us write down the states explicitly, and here I'm going to switch to the shorthand notation. And I should warn you that this is also the first time I'm using the shorthand notation. So if I make any mistakes, please do stop me. So what is the M1, M2 states? The M1, M2 states are, so you would have, for example, 1 half allows 2 possible M1 states, which is 1 half and minus 1 half. And J2 equals 1 allows 3 possible M2 states, which is 1, 0, and minus 1. So the product space can have all possible M1, M2 values. So fixing this equals half, I get 1 half and 1, 1 half 0, 1 half minus 1, minus 1 half 1, minus 1 half 0, and minus 1 half minus 1. Okay, so I get 6 possible states. Is this consistent? Well, let us check. The space has to be 2J1 plus 1 times 2J2 plus 1 dimensional. So this is for J1 equals half, this is 2. And for J2 equals 3 half, this is J1 equals half, this is 2. J2 equals 3 half, this is 4. I get 8. What's going on? What mistake am I making?
सर J1 बराबर तो 1/2 है और J2 बराबर 1 है ना सर?
Yeah, very good. At least somebody is paying attention. So I deliberately put 3 half. The 3 half corresponds to J value, not J2 value. Okay. So this is why this notation can be a little confusing, because you can quickly get lost in what is J2 and what is J, right? So this is actually 2 times 3, which is 6. So our enumeration is actually correct. So let us write down the product space Jm. In Jm, there is 2 different values of J, remember. J can be plus half and J can be 3 half. So for the 3 half states, there is all different values of M. So this is, if I put J equals 3 half, the M value is 3 half, or 1/2 or minus 1/2, right? Because 3/2 minus 1 is 1/2 and 1/2 minus 1 is minus 1/2, and minus 1/2 minus 1 is minus 3/2. And for j equals half, again, there is two possible states, 1/2, 1/2, and 1/2 minus 1/2. Okay, so that again, there is 6 states, and this because it's the exact same 6-dimensional space. And notice the pattern in these different j spaces. You have a highest value of j, and the second highest value of j starts with an m that is the second highest value of m for the first column. So this is column 1, this is column 1, and this is column 2. And in column 2, the highest value of j is the second highest value of j in column 1. That is how the product space works. Okay. Now, since we already know that m1 equals m1 plus m2, we need to understand how to write these 6 states in terms of the 6 m1, m2 states. So how do you write? The question is, how do you write the jm states in terms of as linear combinations of the m1, m2 states? Okay. The answer to this question is basically the Clebsch-Gordon coefficients. So let us actually try to work this out. The way we will work this out is as follows. We will try to, we will start with the highest state in the first column, the jm column, and then we will apply the j minus operator and keep going down. Okay, now we will ask, we'll take the first vector in the first column, which is this vector. Okay, 3/2, 3/2. Now I need to write this vector as a linear combination of the vectors in this set. Okay. Now, if I want to write this as a linear combination, remember that it has to satisfy the property that the addition of these two m1 values should give me the m value of this. The m value of this state is 3/2. So what are the possible states in this m1, m2 set whose addition can possibly give me 3/2? Well, minus 1/2 minus 1 is minus 3/2. So this won't do, right? So similarly, you can keep going up, and you will find that there is only one state in this basis whose m1 and m2 add up to 3/2, and that is the topmost state. Okay. So if you look at the first column and you look at the topmost state, this state is actually unique. There is only one vector, and this is in general true for any addition, not just for 1/2. The topmost state in the first column with the highest value of m in the jm state can only be written as one unique state in the m1, m2 basis with the highest possible values of m1 and m2. Okay. Now this still doesn't fix the state uniquely. For example, I can define this as e to the I5 times the state 1/2 1, right? So the first state. But I usually, the convention is that you don't usually put any phase factors here, and you write this exactly as the m1, m2 state that you're looking at. Okay, this is a convention called the Shortley convention, Gordon-Shortley convention. Okay, so the 3/2, 3/2, the topmost state can only be written as one possible state in the m1, m2 basis. Okay, in the uncoupled basis in another language. Now let us go down and look at the second state in the jm basis. The second state is 3/2, 1/2. This corresponds again to a j value of 3/2 and an m value of 1/2. Now, if I want to get m1 plus m2 equals 1/2, then this state fits the bill, right? Because 1/2 plus 0 is 1/2. And this state also fits the bill because minus 1/2 plus 1 is also 1/2. And the rest won't fit the bill. So somehow I should be able to write this state jm, 3/2, 1/2 as a linear combination of the two states here with m1, m2 adding up to 1/2. So the question is, how do you write this down? So before you actually do this, you actually know roughly that this has to be written as a linear combination of, what are the two states? 1/2 and 0 plus b times minus 1/2 and 1. So we need to figure out, we need to have a procedure by which we can determine what this a and b are. Is the question clear? If there's any questions, please stop and ask. Okay. I'll pull up the chat window here in case someone wants to write down their questions. Okay. So how do I actually do this? Well, now one can always write this 3/2 1/2 state by starting with this state 3/2 3/2 state and applying the J minus operator, right? So J minus acting on 3/2 3/2, you know that this has to be equal to h bar times square root of j times j plus 1, which is 3/2 times 3/2 plus 1, minus m times m minus 1, which is 3/2 3/2 minus 1, 3/2 1/2, right? So this is the usual j. So remember that j minus acting on jm is h bar times j plus 1 minus m minus 1 j n minus 1. I'm using this particular formula here. So j minus acting on 3/2 3/2 can be written as, what is this guy equal to? This is 3/2 plus 3/2. So square root of 2 times 3/2. This is square root of 3. H bar square root of 3, 3/2 1/2. Okay. And you might say, what's the big deal? Because this is something, our job is to write the states in the JM basis as a linear combination of the M1, M2 basis. So what does going down in this ladder gives us? Because we are still writing the one state in the JM basis in terms of the other state in the JM basis. Well, the point is this. Since I know that the top state is very unique in the sense that there is only one state in the M1, M2 basis that corresponds to this, once I fix the top state, I can simply write the top state in terms of the uncoupled basis, M1, M2 basis, and just apply the J minus operator and keep going down, and I can get all states in the JM basis in terms of the M1, M2 basis. This is how it works. So this should be okay, right? Now,
सर
yes. Hello.
यहाँ पे जो अपनी बेसिस थी M1 M2 की थी, J माइनस जब अप्लाई किया था तब अपन,
So here I am only
जब J माइनस अप्लाई होता है M1 M2 पे,
नहीं यहाँ पे JM पे, see J minus can act on, so let me write it in the original form. Okay, J minus, see, remember that these states are simultaneous eigenvectors of J square, Jz, J1 square and J2 square, right? So if I apply J minus on this states, J1, J2, Jm, I will get something J1, J2, Jm minus 1, right? Now I can also write J minus as, this is what I will do, J1 minus plus J2 minus, right? And now
yes,
J1 minus and J2
sir.
minus act on the M1, M2 states, but J minus acts on the Jm states. Okay?
Yes, sir.
Okay. So if there is, I know that this notation can be confusing. So if anybody have any questions, please stop me and ask. Don't wait till the end. Okay. So here's what I'm going to do. So my job, see, I already know what this state is in terms of the M1, M2 states, right? Now I want to understand what this state is in terms of the M1, M2 states. First, let me write this state 3/2 1/2 as 1 over square root of 3 h bar j minus acting on 3/2 3/2. Okay. Now I also know that 3/2 3/2 is basically 1 1/2. So I will write this right hand side of this equation as j minus can be written as j1 minus plus j2 minus acting on 3/2 3/2 in the uncoupled M1 M2 basis is basically the state 1/2 1. Okay. And that is pretty much all I need. I have to write J minus as J1 minus plus J2 minus, and I have to express the topmost state in terms of the M1, M2 states, which I have done. And the topmost state is easy to figure out. There is only one possible state in the other basis that gives you this particular highest value of n. This corresponds to the highest value of m1 and highest value of m2. Now, how does this act on this? Well, remember that this has to be ideally thought of. So I will write this down. This equation should be ideally written as J1 minus direct product 1 plus 1 direct product J2 minus acting on the M1, M2 state. So this is basically J1 1 half direct product 1 1, right? So this is what I'm actually doing, except that I'm writing this in a very shorthand notation that we discussed already. Okay, so when I do it this way, the J1 minus lowers the M1 value by 1 unit and J2 minus lowers the M2 value by 1 unit. So remember that this is my M1 and this is my M2. Okay. So the J1 minus doesn't care about the M2 value and J2 minus doesn't care about the M1 value. So this is equal to 1 half. Now let us first add the state on the J1 minus. J1 minus would make this H bar square root 1 half plus 1 minus 1 half minus 1 minus 1 half 1 plus H bar. J2 minus acting on this state would give me J2 plus 1 minus M2 minus 1 acting on M1 M2 minus 1 is 0. Okay, is this clear? Is this step clear to everybody? So the H bars all cancel out and I get 1 over root 3. What's the first guy? This is 1 half plus 1 half, which is just 1. So 1 over root 3 minus 1 half 1 plus the second guy is square root of 2 over 3 1 half 0. Okay, so I have written the second state in this product basis 3 half 1 half in terms of the M1 M2 basis. So 1 over root 3 minus 1 half 1 plus square root of 2 over 3 1 half 0. So notice that this is already normalized, right? 1/3 plus 2/3 is equal to 1. So I don't have to further normalize this. So that is good. And then you keep going down. Now you act J minus on. So then again you repeat the procedure. Okay, and then act J minus on the state 3 half 1 half. Okay, and then you write this as J1 minus plus J2 minus acting on the states on the right, and then you can figure out what is 3 half minus 1 half in terms of the uncoupled states. I will leave that for you to figure out. Okay, that is simple enough. And in this case, if you look at the very last state in the top column, it turns out that this is also a unique state. Okay, so you'll have to do some work to figure out this state. You'll have to do some work to figure out this state. But to figure out this state and this state, you don't have to do much work because you can simply use the fact that M1 plus M2 has to be equal to M. And just like there was only one unique state whose M1 and M2 added up to 3 half, there is also only one unique state for which M1 plus M2 adds up to minus 3 half. Okay, and that state, for example, in this particular case, is this. Okay, this is the only state in which the M1 and M2 values add up to minus 3 half. Okay, so I can write the lowest state in the first column also as a unique state. 3 half minus 3 half is basically just minus 1 half minus 1 in the uncoupled basis. Okay, and these are basically the Clebsch-Gordon coefficients for this problem, right? So I will put a box around this equation and I will write it in the original symbol and we will read off the Clebsch-Gordon coefficients. Okay, so the left hand side of this boxed equation basically is J1, J2, which is 1 half 1, Jm, which is 3 half 1 half, equals 1 over root 3, J1, J2, again 1 half 1, M1, M2, which is minus 1 half 1, plus square root of 2 thirds, 1 half 1, J1, J2, M1, M2. Okay, so this is what I mean. So which means the Clebsch-Gordon coefficient, for example, 1 half 1, 3 half, 1 half, 1 half 1, minus 1 half 1. If I take the inner product of these two guys, if you take this equation, you get this to be 1 over root 3. Okay, similarly, 1 half 1, 3 half, 1 half, and 1 half 1, 1 0 turns out to be square root of 2 thirds, and so on and so forth. So this is how you deal with the first column. The first column, you basically start with the topmost guy, which is a unique vector, and then apply the j minus and get the second state. And then knowing the first state and writing j minus as j1 minus plus j2 minus, you can figure out the linear combination corresponding to the second guy. And similarly, we keep going down. Okay. Of course, for more complicated additions, this becomes a rather lengthy process, but this is the general procedure. Okay. Now let us go to the second column. Look at the second column, first vector. This corresponds to a j value of 1 half, j value of 1 half, and m value of 1 half. Which means if I simply apply the rule that m has to be m1 plus m2, right? I can guess that this also has to be written as some linear combination of this form. Do you understand? Because this also corresponds to m value of 1 half. The point is, in the Jm states, there can be different j's that correspond to the same values of m. In fact, there is a degeneracy in the Jm basis. There can be different values of j that admit the same values of m. For example, if you have a j value of 3 half, it admits an m value of 1 half. If you have a j value of 5 half, that also admits an m value of 1 half, and so on and so forth, right? So there can be different values of j that corresponds to the same value of m. So now how do I figure out, for example, what the linear combination is corresponding to the 1 half state? I will demand two things. I know a priori that this state should also be written as a linear combination of the 1 half 0 and 1 half minus 1 half 1. I will simply demand that this state be normalized and this state be orthogonal to the 3 half 1 half state. Why should it be orthogonal? Well, because it corresponds to a completely different value of j, so there can possibly be no overlap between the two states. So I will demand that there is no overlap between these two states. In other words, I will demand them to be completely orthogonal, and then I will demand the state to be normalized. And if I demand these two guys, this state is uniquely fixed. So for example, my 3 half 1 half state we figured out was 1 over root 3, right? Minus 1 half 1 plus square root of 2 over 3, 1 half 0, right? Now my 1 half state, this Jm state should also be a linear combination of these two states, but it has to be orthogonal to this guy. So I will write this as square root of 2 thirds minus 1 half 1 minus square root 1 third 1 half 0. That's it. Just by inspection, I can write this down by simply demanding that this is orthogonal to the previous state. Okay, you can quickly check that this is indeed orthogonal to the previous state. So there is also some conventions you employ in writing down this Clebsch-Gordon coefficients. And one of the conventions that is employed is that all these coefficients are real quantities. Okay. So there is no need a priori for this convention. For example, I can introduce arbitrary e to the I5 over here, and the same e to the I5 over here, and or some combinations of faces everywhere, such that these twin constraints are still satisfied, that the states are orthogonal and they're normalized to unity. But we don't do these things, and we simply demand that all these coefficients are real. Okay. In other words, what I'm saying is that this basis transformation that is supposed to be unitary transformation, unitarity simply means the matrix is the U dagger is the same, U dagger is equal to 1, but since they're all completely real, U dagger is the same as U transpose. That is all I'm saying. So this is a convention that is chosen, and we will stick to this convention because it makes our life easy. Okay, so now we'll have to figure out what the next state is in the second column, which is 1/2 minus 1/2. Okay, you can figure it out in two different ways. You can simply, once if you have already figured out 3/2 minus 1/2 state, you simply choose the orthogonal combination to 3/2 minus 1/2 and you're done. Okay, or you can do the elaborate procedure where you apply j minus to this state and go down. And since you know what this state is already, you can write the j minus as j1 minus and j plus j2 minus and figure out the 1/2 minus 1/2 state. So this is the general procedure in which you solve for the Clebsch-Gordon coefficient as a practical matter. For specific examples, you look at the highest j value and the topmost state in the highest j value, and that is a unique vector. Okay, you just take that vector, apply j minus, keep going down, and write j minus as j1 minus plus j2 minus and figure out the other linear combinations. And when you come to the second column, the topmost vector in the second column, there is another vector in the first column that has the exact same m value as this guy. So simply choose the orthogonal combination and you're done. Okay, and then go down the second column and so on and so forth. For example, if I add two j values, that gives me three possible j values, then I'll have a third column here. And the third column, I will again do the exact same way. The topmost vector in the third column, I will take that and take the other vectors in the first two columns. So suppose if, let us say I'm adding, let us say j1 equals 3/2 and j2 equals, let us say 1. Okay. Now, what are the possible values of j? 3/2 minus 1 is, let us actually give it something. So let us say 2. What is 2 minus 3/2? So this is 1/2. 1/2. And 2 plus 3/2 is 7/2. And with spaces of, let us say, spaces of 1. So then the next guy is 3/2, next guy is 5/2. So we'll have 4 particular columns here, right? So let us write the highest j value. So that is the 7/2. So the topmost state here is 7/2, 7/2. Then 7/2, 5/2, 7/2, 3/2, 7/2, 1/2, 7/2, and you just keep going down like this till you reach 7/2 minus 7/2. Okay. Now the second, this is j equals 7/2. Then j equals 5/2. The topmost state corresponds to the m value 5/2, 5/2, 3/2, and so on and so forth. Then j equals 3/2. The topmost state corresponds to 3/2, 3/2, 3/2, 1/2, and so on and so forth. And j equals 1/2. The topmost state corresponds to 1/2, 1/2. Okay. So this guy is unique. So you know what this state is, and using this, you can figure out this as a linear combination of the J1, M1, M2 states. And to figure out the 5/2, 5/2 state, you just take this guy and take the orthogonal combination. Okay. Same here for the 5/2, 3/2 state, you take this guy and take the orthogonal combination. But what about this guy? Look, now there is 3 states that have the same m value, 3 states with three different values of j that have the exact same m value, right? Now you have to choose this state such that it is orthogonal to both this guy and this. So this guy and this guy, and is also properly normalized. Okay, and so on and so forth. So in more complicated examples, when you have multiple columns, you can have, for example, 3 or 4 or 5 different values of m, five values of j that has the same value of m. And in those cases, as you go from one column to the other, you have to always ensure that states having the same m value are always orthogonal to the state with a different value of j having the exact same m value. Okay. So this is, I mean, of course, we don't practically do very complicated examples like this, but in principle, if you want to do it, this is how you do it. Okay. So there was, yes.
Sir, when you are talking about the unitary transformation, okay, is it the only m equal to m1 plus m2? Is it the only constraint, or there is a lot of other constraint? Because
There
I
is
don't.
there is not a lot of other constraints. For example, if I apply this procedure and I keep going, how will I get a negative m values, right? So it turns out that you only have to figure out till m equals 0, because the Clebsch-Gordon coefficients corresponding to the negative m values can be understood as, for example, some multiple of the corresponding Clebsch-Gordon coefficients with the positive m values, right? So what I'm saying is, suppose if you have J1, J2, Jm, excuse me, Jm, J1, J2, M1, M2, this is equal to something times J1, J2, Jm, J1, J2 minus M1 minus M2. Okay. So to figure out the Clebsch-Gordon coefficients with negative m values, sorry, this is minus m. To figure out the Clebsch-Gordon coefficient with the corresponding negative values of m, I think this is equal to some minus 1 times j1 plus j2 minus j, or something like that, if I remember right. So there's also additional properties of the Clebsch-Gordon coefficients that helps you determine the Clebsch-Gordon coefficients. This is actually very useful, because if you have a more complicated addition, you don't have to do everything. You just have to work out till m equals 0, and all the other negative m values you simply can read from this particular expression. Okay, all the other Clebsch-Gordon coefficients can be understood as this. So there is three basic important properties that you have to figure out, that you have to remember. One is this guy that I just told you. The second is m1 plus m2 has to be equal to m. The third, of course, is the addition of j1 and j2 admits all possible values of j from j1 minus j2 to j1 plus j2. As far as I can remember, there is not much else that you have to remember. But within these three, pretty much everything is covered, and you can figure out this basis transformation uniquely, with the proviso that you demand all the Clebsch-Gordon coefficients to be real. That is a convention you employ. Okay, there is no phases employed.
Okay, sir.
Any other questions or comments? So I will try to put up a problem sheet, but even if I don't, please try to complete this problem for the addition of 1/2 and 1. This is basically the problem sheet. So you don't have to wait for me to put out the problem sheet. Please complete this problem fully and figure out everything, uh, all the Clebsch-Gordon coefficients for this particular problem. Why do we call this a unitary transformation between the two bases? Well, we call this a unitary transformation because, remember, the basics of quantum mechanics, right? So we always claim that a basis set is not unique, right? I can always go from one basis set to another basis set. So I can always, suppose if I have a basis set EI, I can always go to a basis set EI prime. Okay, but so for example, if I write down any matrix element in the first basis set, suppose if I have a vector, suppose if the probability of some state psi I going to the state psi f, right? These probabilities have to remain unaltered because of this basis transformation, right? So regardless of how I enumerate my Hilbert space, the answers to physical processes cannot be different, right? This is the fundamental rule that one has to employ when figuring out this basis transformations. So whether I use EI or EI prime, the chance that an atom will emit a photon and go down to a ground state, the probability for that process should be the same regardless of what basis vectors I employ. Otherwise, there is something seriously wrong with my formulation. So the kind of basis transformation that ensures that this property is a unitary transformation. Why is that? Because I write psi I as some linear combination of AI, EI, and I write psi F as some linear combination uh, AF, EI. This is a very bad notation, right? BI, EI, right? Now, psi F, psi I is basically a BI star AI, right? But I want, suppose if I express this in terms of the primed basis, I will write psi I as some AI prime, EI prime, and psi F as some BI prime, EI prime. then I want psi f, the actual value of psi f psi I to be the same as psi f prime psi I prime, excuse me, to be the same as psi f psi I, right? Agreed. So suppose if the transformation from, let us say, ei prime can be thought of as u times ei, where u is some matrix, then psi f prime psi I prime in compact notation can be written as uh, psi f u dagger u psi I, like this, right? Psi f psi I. Now, if I do any basis transformation, then of course this amplitude will not be guaranteed to be equal. But if I choose a transformation for which u dagger u is 1, then this two would be exactly equal. So those are the kinds of transformations we employ in a basis transformation. That is why unitary transformations are important. So for this particular problem, regardless of what kind of basis vectors are used to describe my product space, whether I choose simultaneous eigenvectors of this four set of operators or that four set of operators, if I calculate any physical quantities, I should get the exact same values. That is why I demand that the transformation between these two basis sets should be a unitary transformation, not any random transformation. Okay, so I think we will stop at this stage now, and I think this formally concludes our discussions on angular momentum.